Hi everyone, I am Cynthia Hartley and this video is a walkthrough of the tutorial for Chapter 10 in the Mastering ArcGIS Pro textbook. The software version I'm using is 2.6.1. Make a note if that's different than what you have, and don't worry if things don't always look the same. The chapter we are doing this week is Joins and Overlays. So we're going to start with the first two sections, which I'm going to combine together, understanding spatial joins and managing cardinality. These two sections really go together. So we're going to do steps 1 through 11, and then we'll take a break and give you a chance to practice some of the steps. And just a reminder, hopefully you're planning enough time that you can do this tutorial with breaks, potentially. You really don't want to have to do these straight through. You get really tired towards the end. I know my attention starts to wander. I have a hard time focusing and really absorbing what I'm doing. So plan breaks, and if you need to, step away and come back fresh. So let's start by opening up our project that's been provided for this class. I'm keeping my data on my C drive. So I'm going to open up the data that we downloaded. And what we're looking for this week is in class projects. And we want the overlay analysis. So I'm going to double click that. Once you're here, open up your ArcGIS project file, overlay analysis. So here we are. You should have something that looks like this after you get your project open. Zoom out and take a look at what we've got here. This should all be familiar. You all spent a couple weeks ago a lot of time digitizing these geology layers. So this week we're going to use this data to do some joining and some overlays. I'm going to start by cleaning up this display so it's not quite so busy. Let's turn off city limits, and I'm just going to collapse the layers that we're not working with right off, just to clean up my contents pane so I can see what we're working with. I just moved geology up underneath wells. Wells and geology are the first two layers we're looking at today. And if you expand geology, you can see there's quite a lot of, see we're symbolized on unit name. We've got quite a lot of different layers here, so our attributes. So let's just collapse this to simplify. So what we're looking at here is, of course, our geology layers, and then these red dots are wells in, of course, in the Austin, Texas area. And what our first task is to do is to associate the geology units with each of these wells. So what this means is we're going to want an output table of the wells, and then we're going to have a column that's going to have these geology units with it. So to us, what that means is that the wells is the target layer in this case, in this join that we're going to do. We're going to join the attributes from the geology table, the geology layer, to the wells. So that gives us what kind of cardinality. We're going to have many wells, and each well is going to have one geologic unit. So it's a many to one join. So as you're going to learn as we go, this is a pretty simple join. So let's start. What we want to do is open up our spatial join tool, and my geoprocessing pane's already open. There's my spatial join tool right there. And then if it's not in this list here, just type it in under Find Tool. So let's just go ahead and open this up. We're going to set our target features to wells. Our join features is going to be geology. And let's rename our output feature class. So in the text, they have you do wells geology all lowercase. I have my own kind of way I like to do this. So I can see the words better. I'm just capitalizing the first letter of each word. So wells geology. And then it's already set here, join 1 to 1. And we want to uncheck this box. And just a reminder, if you're ever not sure what to put into any of these parameter fields, just mouse over the information icon. And that will tell you, give you information, help you make a decision on what to do. In this case, we don't want to keep any features that don't happen to fall into a geology area. So this will just keep our output cleaner. It'll eliminate any null values that might show up. So let's take a look at the wells attribute table. Since this is the one that we're going to be appending the geology attributes to. And as we scroll over, there's quite a lot here. So we're gonna clean this up in our tool so that we don't have a lot of data that we don't need. So as we are getting set up here, we're creating a new feature class. We're not actually bringing data into the wells table, but we're making a new one. So with this tool, we can cut down on everything that we bring across. So again, here are all of these fields. So this first one is the wells layer, and then if you go all the way down, toggle down and down, here's this geology layer. It's where everything's capitalized. This one's a bit simpler. So let's start by removing some of these from the list. We're actually only going to keep 3 of the features that go with the wells. So this county code is going to go, state well numbers we're going to keep. So you can see there's a red X. So that deletes it. To save a little bit of work and going down and Xing on everything. The next thing that we're going to keep is aquifer code. So we're just going to, I clicked up here on GMA. We're going to get actually basin we're going to get rid of. And let's look for aquifer. So here's aquifer code. We're keeping that. So I'm going to hit shift click. And that highlights everything here. I'm going to hit an X. It's going to delete everything. So we have state well aquifer code. And the next thing we're going to keep is well depth. So I'm going to click on that. Here's well depth. So I'm going to right click and click on well type right above depth. I'm going to X that out. That goes. And then we're going to get rid of the rest of everything that's associated with the wells feature class. So down to username. Shift click and X that out. So that really cleans up the data that's going to come across into this new feature class we're creating. So then we're also going to delete a bunch from the geology layer. The only thing we're keeping here is going to be origin label, which is this one here. So again, I'm going to shift click and get rid of all of those, keeping origin label. And then I'm going to get rid of we're going to keep unit name. So we can get rid of shape length and area. So this is what your table should look like. If you messed up and you deleted something that you shouldn't have, you can go over here to reset, and this will repopulate everything back. You're not getting rid of any rows in your tables. You're just setting up this tool so it's only going to bring across this information. So there's one more thing we need to set up. I'm going to collapse this just for a minute to simplify this. This is where what I have on my tool. It's a little different than what's in the book. We need to set up our match option to within. So if you think about that, we're looking for all the wells that are within the geology units. So within. We're not going to worry about anything that's on the border. It's very unlikely that we're going to have a well that's exactly right on the border between these geology units. XY coordinates, which is what a point is, which is what our wells are dimensionless, so they take up no space. So the chances that we're going to lose one of the wells is just not something we're going to worry about. Okay, so I'm going to expand that again. So this is where it's a little different. Match option is above my fields. In the textbook, it's below the fields. So it's just something that is a little different between software versions. We don't have to do any merge rules, so I think we're ready to go. Go ahead and hit run on your tool. Okay, so my tool has run. Let's take a look at our new feature class that we created. And I'm going to zoom out here on my map. I'm going to turn off the old wells layer. So here's my new layer and the wells geology, which we can read pretty clearly. If I turn that off, yeah, so that looks good. So let's open up this attribute table and take a look at what came across. Yeah, so this is all of the data that we selected. So we really simplified this table quite a lot. And let's do a little search and see if this worked out the way it should have. We're going to figure out how many of these unit names have limestone. So let's click back on our geoprocessing tool. What we want to do is look for the layer, select layer by attribute tool, which I don't have in my list. So I'm just going to type it in to my search box by attribute. Select layer by attribute. So that's the tool I want. So my input row, I have wells geology highlighted, selected. So it's going to select from that table. Actually, I highlighted it there. So it's going to be a new selection, and let's type in an expression that will give us anything that has limestone in it. So we're going to select the field unit name. We just want contains in this part. Contains the text. So this is where we need to make sure it's capitalized, limestone. If you type in limestone and it's not capitalized, you're going to get a different answer. So just do a quick check. Now, if you did inadvertently type in limestone and it wasn't capitalized, when you check your SQL, it's going to give you this. It's going to tell you your SQL expression is valid, but no records were returned. So that's sort of a red flag that something's wrong. So let's put that back. So run the tool. And I'm just going to turn on the values that are selected. So here's all my limestones. You should have gotten something that looks like this. Actually, you should have gotten something that looks exactly like this. Okay. So let's clear our selection and close our table. This brings us to the end of the first section. This was, we just did step 3. So before we move on, be sure to remember to save your project. I'm going to save mine right now before we get going. So we're going to shift gears. We're going to start on the next section. This is going to be step 4 in managing cardinality options. So let's get our display set up with the layers that we're going to use. I'm just going to collapse these wells. And what we're going to use now are creeks and soils. So let's zoom in a little bit so we can see what we're looking at. And let's also, I'm going to open up the symbology here. And let's look at our tables. This is always a good idea while we're getting acquainted with our data, just to see what we've got. This layer we'll be working with MUID. I'm not really sure what that stands for, but ID is no doubt that's some kind of an identification number. Looks like it's a state, Texas. That's going to be this one here, MUID. And then a whole bunch of other attribute data. These are a bunch of numbers that we're going to be working with. And let's look at creeks. I'm just going to have both those tables open and handy. Stream name. Yeah, not too much here. I think we're just interested in the stream names. So what our task is, still want my tables open, but I want to be able to see my display. Our task is that we've got all of these creeks that cross through these different soil types. And what we're interested in now is permeability of the soils. We want to know actually infiltration. So if we've got soil that has a high infiltration rate, then that's going to recharge the groundwater in the wells quicker. So we want to create kind of a similar situation, what we did with the wells in the geology. We want to look at our creeks, create a new layer, and associate soil filtration rates with that. So it seems kind of similar to what we did with the wells in the geology. So we're going to try that approach and we're going to see how that works for us. So I'm going to go back in my geoprocessing tool and I want to find the layer I was working, or the tool I was working with. So here I am in my favorites and it's my spatial join. So I'm going to open that tool up. I'm going to set the target to creeks. I'm going to try to set the targets to creeks. Creeks, so that's my target. This is the data that I'm going to bring in the soils data on. So we're going to join this to soils. And we're going to give this a name. Creeks, soils. So those are my two layers, and I'm just going to do an underscore within. Oops. Within. So we're going to stay with a one-to-one join. So for each record in the creeks layer, we're going to join it to one record from the soils layer. And moving down the line, we're going to uncheck our keep all targets. And then even though this is a little out of order from the book, we're going to change this to within because that's, so what we're going to do is we're going to come here into the soil layer, and any of these creeks that are within, completely within one of these soil polygons, that's going to be our match option. So we're going to clean up our fields. We are going to delete watershed. Shape length. Area. Perimeter. And then now we're down into the, here we are in the soils layer. We're going to, this is this MUID that we're interested in. And then we're going to delete the next one, row. MUID1 and state. So we're going to keep all of these attributes. These were all those number attributes we were looking at. And we're going to go all the way down. We're going to delete these three shape attributes. Okay. Let's get back up where we can see things. I'm going to collapse this to clean it up. The book says to change this to within, and now we're going to run our tool. So let's open up our new table and see what we have. So it looks like everything came across. We're happy with that, but let's see what this actually looks like. So let's change the symbology, move that down so we can see. So here's our creek soils within, and let's just give that a color that stands out from the blue of the other layer. Just go for any of these. So not all of our creeks came across. In fact, it's quite patchy. And if you look closely, what's happened here is the only creeks that have come across are ones that don't cross one of these boundaries. So because of the rules we set up for this join, we're only getting creeks that are entirely within and not crossing over a soils layer. So if I click on that, you can see that that layer, let's do a select. This layer crosses this boundary, but this one doesn't. So in this case, because we're working with lines that have dimension and cross all the way through and across the polygons, it wasn't the correct choice. So again, let's look at these tables. So here's our creek soils within. We have 306. If we go over to creeks, our original 381. So it actually filtered out some of our creeks, which is not what we wanted to do. So what we're going to do is we're going to try to use a different way of combining these. Let me close our symbology. Instead of doing the within, we're going to try to use intersect. So the risk that we run with this, though, is that we might be in a situation where we have a one-to-many join, and that breaks the rule of cardinality. However, they're using the merge fields, we can get around that. We can still do keep our one-to-one. So let's do that. Let me show you something that's kind of a cool feature. So the soil identification attribute, the MUID field that we were looking at before, we can take a quick look at it now. It's this one. So this is text. And we can just combine, we can take each one of these that goes to a creek. So if we have one creek that crosses multiple different soil layers or polygons and has multiple different categorizations, we can actually combine that into one field. So we're going to do that right now. So let's see, get back to our map so we can see what's going on with that. I want to clear my selections. Okay. So our spatial join tool is still open. We're just going to change things a little bit and rerun our tool. We're going to leave our target and our join feature the same. Let's just give our output feature class a new name so we don't overwrite the old one. So we're going to keep soils creeks, creeks soil, and change it to int for intersect. So our join operation is one-to-one, and then our match option is intersect all the way up here at the top. So let's open up our fields options. So this first one, and just to go back and refresh our memory, this AWC is, that's a number field. So we're going to select that And our merge rule is going to be to calculate the mean. If, for example, we have a creek that crosses multiple soil polygons and we need to combine multiple different numbers, what this is going to do, it's going to take the mean of those numbers. So we want to do that for all of these. And the book tells me that I can click and highlight all of these and it will work. But when I tried it, it didn't. So I'm just going to go through here one by one and select all of these attributes and tell it to do the mean. If you can make it work without having to do that, go for it. Move this down. So if this is a number field, it'll merge rules. It'll give you options of things you can do with numbers. If it's a text field, you won't have these options. So it looks like I got everything. I'm going to take the mean of all of these values if they get combined. So now we have to figure out a way to deal with this MUID, which is a text field. Actually, we're going to deal with this MUID right here. So let's go back up here. We're going to create a new output field. So click plus next to that, and our new field is going to be called MUID join. Oops. So it's red because we have to set some properties. So that's highlighted. I'm going to toggle this up and we're going to go to properties. So here's this field. You can see that it is indeed a text field, and then it's the length. We want to control that so it's not the chance to put so many letters into it. And now we want to go back up here and we're going to go over to the source heading. And our merge rule is going to be to join. And then our delimiter is going to be a comma. So what that's going to do as we join this table in our new output, if one of these streams crosses multiple soil polygons, it's just going to add each one of these MUID text entries. And then the next one it'll put in after a comma, and then the next one. So it'll just stack them up essentially into one field. So now we're going to open up this add new source and come down here and click on soil so we can see everything that's in here. Oops. And then where it says add selected, we're going to click on this here, this MUID, and we're going to add selected. So this is essentially figure 10.19 in the textbook, although my table is kind of big, so I can't quite see it all. But yours should look something like this. And I'm going to run my tool. So let me just close these tables so we can see more. So here's my new table. I'm going to turn off creeks. So here's the new table, and it looks pretty good. That's the old one. So you can see that it looks like it brought all the creeks across. I'm going to open this attribute table. What we want to look at is what happened in this new field that we created. Here we go, MUID join. So you can see it did indeed put a comma in between all of its different IDs, soil type IDs. and it just stacked them up in ones that cross multiple soil. So let's, I'm going to right click on this and we're going to sort descending. And looking over on the right on this table, so all of these number fields, these would be the mean of multiple fields that were combined for apparently this string crossed two different soil types. So these would be the mean of those two values. And then we can look over here at join count. Let's do that. Let's sort descending here. So here we had 5. This creek crossed 5 different soil types, and there they are here. So let's symbolize. I'm going to symbolize our new table. So I'm just going to open up the symbology, and we're going to do graduated colors. And the field we're going to symbolize is going to be this group. I don't know what that is, HY group. And let's pick a light to dark. Just do that one. And of course, not liking the natural breaks too much. Let's look at quantile and see how that goes for us. So if we look down here at our values, the higher the value, the higher the infiltration rate. So let's I want to make these lines thicker. So I'm just going to do this. I'm going to go into more and format all symbols. Let's go back. Oops. Two points. Apply. So that kept the colors. That just changed the line thickness for all of these. Okay, so that's the end of step 8. Now on step 9, what we're going to do is we're going to look at a way that we can kind of force a one-to-one relationship. We're going to actually create we're going to create multiple copies in the target feature table. So let's go back to I'm going to close symbology. Back to geoprocessing. So we've got our spatial join tool still here. We're going to change the output name again, and this time we're going to change it to, we're going to keep this, but we're going to change it to many. So I'm just going to do another underscore, many. And that's because we're changing our join operation from one to many. So let's run. And now let's open our table and see what we've got. So in our join count, we're going to sort this ascending. So looking over here, so this is our target FID or feature ID number. We now have duplicate 3s, and we've got 3 7s. So these were the original FIDs. They're now have been replicated, and you can see that they have different. They're associated with different MUIDs over here. So each one of these are unique for 7, 71, 150, 35. And we now have 488 records. Our old, let's open this one just to prove it. This one has 381. Okay, so we looked at two ways of dealing with this one-to-many cardinality, and this one has created duplicate records. The last one we did stacked up these MUIDs into one feature here. Neither one of these are really optimal. There's a third way to do that we're going to look at right now. So I'm going to close this. And what we're going to look at now is the intersect tool. So let's go back to our geoprocessing. And I'm just, here it is. It's in my list. If you don't have it in your list, you can just type it in up here. I'm going to open up this tool. So what this tool is going to do, it's actually going to split the creeks where they cross the different soil types. So we're going to put our input features as creeks. And then it gives us another drop down, and we're going to put in soil types. Down here, soils. I'm just going to take out this underscore. Creeks intersect. We're going to run our tool. So there's our layer. And what we're going to do is I'm going to symbolize it. I'm going to symbolize it the same as this. So let's go into symbology. And I'm going to show you a way to do this quickly. Come up here. So I'm in the just the main window for formatting the symbology. Let's see. Sorry, go back here. Primary symbology. Import symbology. And we're going to import the creek soils int layer. So this is the layer that we're symbolizing. This one here. So it's populated these fields already from this layer. We'll run it. So here's our new layer. Turn that on. So it is a little different. It might be easier to see and visualize if we take off that one. And let's take off our soils. And I'm just going to toggle this back and forth. Yeah. So turning on the soils and turning off the other layer. So we just want to look at our new layer that we created. What we're going to see here is that everywhere these creeks crossed a boundary, it was split into a new feature. So that brings us to the end of this section. Be sure to save your project. We just looked at 3 different ways to deal with one-to-many relationships, and it makes a difference which way you select to deal with them based on whether you're working with points and polygons, line features that cross boundaries of polygons. All right, so we are going to pause here and give you a chance to stop and repeat steps 1 to 11 if you need to go over it again. Just be sure that you understand how to deal with one-to-one and one-to-many cardinality. We just did joining points to polygons and lines to polygons. You will need to understand this for your homework. Okay, so we are going to move on. We're going to do steps 12 through 20. So it's combining 2 sections, merged point to polygon joins and distance joins. So back to our map. Let's go ahead and clean up what we did before. I'm going to just collapse and turn off layers. Let's just go ahead and take out all of these layers that we created in the first section. So we're not going to delete them, we're only going to remove. So when we remove something from the contents pane, it just takes it off the map. If you would delete it from the catalog, from your geodatabase, then that's when you're in trouble if you didn't need to do that. So we are going to be working with watersheds and block population. The book doesn't say to do this, but I'm going to move these close together so I can look at them at the same time in my contents. So let's consider these layers that we're going to be working with. I'm going to expand the symbology and open up the table. So I'm opening up this watershed table. And what we see here is, this is probably what we're really interested in. Here's the names of each of these watersheds. So let's bring this down. So each of these outlines defines one watershed. So this is an area with many watersheds that come together. And let's look at our block population. So what this is, this comes from the Census Bureau, and it's a point layer, but it looks like it was derived probably from a polygon layer that was blocks, so population blocks. So what we've got here, here's a block number, and here's a population over here. Let's expand. Population 2010. So this would be the number of people within each one of these blocks. So we've got population, number of households, a number of housing units. So this is the smallest unit that the Census Bureau uses. Let's see, let's open the metadata. So here's a description of it. So if you ever are wondering more details about any of the layers, you can always open up the metadata. And here this explains that this is populations in 2010 from the Census Bureau. And basically these are the points are centroids. So it's a central point for each of these blocks. Let's close this. So what our task is to figure out how many people, what the population density is for each of these watersheds. As we know, if there's a lot of people, a very high concentration of population density, then it's going to create pollution in the runoff. So we want to look at all of these watersheds and figure out what the population density is for each so we can do a pollution study. So what we need to think about is how the table is going to look, because that will tell us what tools to use. So what we want is a list of the watersheds. So that's going to be our target layer. And then we're going to merge into that the population numbers. So it's actually a one-to-many. So one watershed to many centroids. But we want to merge those centroids. So the join is actually a one-to-one. So let's set that up. So close the tables that we opened. Let's go into geoprocessing. And if you haven't figured this out yet, it's really useful to understand what's going on over here. So these are tools I've been using. And there's a drop-down icon here. It says Open History. So if you open this up, this records all the different times I've used this tool in the past. So if I ever need to go back, I can click on this. It'll open up this tool and it'll save all of these parameters. It'll be set to the way I used it before. So that's useful if you need to, perhaps for your homework, you forgot to get a screen grab of something, you can go back and you can recapture it here. Okay, so we're going to start with spatial join. We're going to start fresh. So I'm just going to open up this tool from here. So here's our blank tool. Let's go ahead and set this up. Our target feature is watersheds. Our join feature, block population. We're going to change this name to something we are controlling. So it's going to be watersheds population. So we'll abbreviate that to POP. And here we're going to go with a one-to-one join, even though the cardinality of our layers is one-to-many. We're going to force this into a one-to-one. So that means we're going to have to set up some merge conditions. We're going to uncheck keep all target features. What this means is if there are any features that are empty, that don't find a match, then we're not going to keep them. So we don't want any null values. And then our match option, this is out of order from the book a little bit. It's above the merge tools. We're going to go ahead and set that right now. So instead of intersect, contains. So, and for the record, if you pick something that doesn't work, I think within will not work. You're gonna get this warning that tells you that you can't use this layer. So if this happens, there's nothing wrong with the software. It means you need to go back and reconsider why that won't work. So for within, right? So for within, we have to specify a certain distance, and we're not doing that. We're doing contains, and that works. So let's set up our field map now. So we're only going to bring across a select number of these columns. So we're only going to keep this one. We're going to start with DCM dash code. We're keeping that. So I'm going to delete these fields above it. We're keeping, and the name, that's the only thing we're keeping from the watershed layer. So I'm going to shift click and highlight all of these down to shape area. That's the last one in watersheds, and delete those. Now this is our block groups, and we're only going to keep 3 from here. So we're going to start with population 2010 to keep. So I'm going to shift click and delete all of those above it. And then we're keeping households and house units. So now we set up our merge rules. All of these values from the block pops, the block population, all of these values from block population, we're going to sum. So I'm going to select each one and set the merge rule to sum. So now think about this as we're doing it. What that's doing, it's forcing our one-to-one relationship. So it's going to take all of these values from block population, and it's going to sum them up and associate them with this watershed. So run our tool. So let's drag this above the layer we just created. So watersheds pop above block population, and open up that table. And let's see if it worked. Yeah, so this looks pretty good. So we've got our watershed code and name, and here's our values that came in from the block populations. And so these are summed for each of these watersheds. So let's symbolize our new layer based on the numbers. I'm going to turn off watersheds, and we're going to symbolize our watersheds pop with graduated colors. So I just double clicked on my symbol, and I'm going to go back to the primary symbology group. Oops. And we're going to select graduated colors. And this is a pretty shocking color combination. So we're going to change that here in a minute. And one thing we have to think about, I'm going to drag the block populations up here so we can look at this. Because we're interested in how many people are in each watershed, the larger number of people in a watershed, potentially greater amount of runoff. So this is a case where it's really important to normalize your data. So we're going to divide the population by the area of the watershed. So you can see this watershed here is quite large, and it's only got a little cluster of block populations here, whereas some of these very small watersheds that are very densely populated, it's going to make a difference. And if we went by absolute numbers, that would be misrepresenting the data. So let's start setting up our colors. So I had block populations highlighted, and I went into symbology and started messing around. So it started resymbolizing my symbology. That's not what I meant to do. So let's go back to, I just want tiny dots for this one. So I'm going to make this small. That's actually pretty good. I'm going to switch that back to a dark color. So now I want to switch to watersheds. I'll symbolize that. So we want to do this on the population 2010. And we need to normalize this based on the area. So go down here to shape area, and it's going to divide our population numbers by the area. And we'll talk about this in a minute. This is if you were to have this show up on a test or a homework to turn in a map, you would need to change this. But let's finish our symbology first. I'm going to change the color scheme to, let's do to blue to purple. The book shows it in green. If you look in your book on figure 10.21, that's what we're trying to approximate. And it looks like they did pick natural breaks. As ever, you always want to think about your method of classification. I think a natural breaks actually works for this because it gives us differences over our area instead of everything being all one color. So let's just go ahead and stick with that for now. And this does look approximately what the book has. The book used green, and to me, green represents trees and vegetation, not population density. So that's why I went with this kind of purple color. Go ahead and play with this and pick a color that works for you. And let's get an answer to what's going on over here. These numbers are, this represents people per area. And these are kind of crazy numbers. So I think I know the reason why. We're going to look at the unit of area on this map, on this projection. Yeah, so this is it here. So our unit is in feet. So what we're looking at is we've got this fraction of a person in a foot in these kind of less dense areas, and in our really high density watersheds, we have 0.0002 person per foot. So you would never represent your data that way. And we're not going to do it now. You would have to go into your table and create a new field that would give you the area in a better unit in your table. So you do a new field and calculate geometry, and then you would select something like acres or square miles or a much better unit. And then you would use that new field to normalize. So instead of the shape area that gives you feet, you would be using acres, and your numbers over here would make a lot more sense. Okay, so compare your map if you've set it up to figure 10.21 on page 329 in the text, and see if it approximates what the text is showing. And let's get set up for the next section, distance joins. This starts on step 16. So turn off the layers that we were using before. And the layers we're interested in now are going to be streets and post offices. go. And just for convenience, I'll bring up streets underneath post offices. And just to make this a little tighter, let's turn on city limits. Just that line's a little bold, so I'm going to cut it down to a 1-point line. Okay, that looks pretty good. Okay, so the setup for distance joins, starting with step 16, we're doing an analysis of post office usage. And what we're interested in finding out is for each street, which is the closest post office, assuming that people are going to go to the closest post office from where they live. And let's go through the thought process of setting this up and get used to doing this, because it'll come in handy on the homework. In order to do the homework, you'll need to be able to think through these problems. So what we're going to want is a list of streets and a field associated with each street that tells us which is the closest post office. So first off, the target is going to be streets, and the join feature is going to be post offices. And the operator that we're interested in using is going to be closest, right? We want to know which post office is closest. So that's going to be just a one-to-one join. It's not like when we do this join, we're going to have a selection of lots of different post offices. Instead, it's just going to be one choice. So it's a simple one-to-one relationship. So we're not going to have to set up any merge rules. So let's go to our geoprocessing. We want to start with a brand new tool. So I'm just going to hit the back and reopen spatial joins. So let's set things up. Target is going to be streets. Our join feature is post offices. And let's give this a better name. Streets post. Join is one-to-one. We're going to keep that. And in this case, we are going to keep all of our target features. And here we go with our match options. In this case, we want closest. All the way down here at the bottom. And distance field name, we have to name this. And if we mouse over, this gives us information why we need to name it. This is going to be, this name's going to be added to the output feature class, and it's going to tell us the distance, the actual distance to the feature, the join feature. So we're going to call this PO for post office distance. And up here, search radius, we're not searching in a distance. And fields, we're going to keep all of our fields. We could, if we wanted to, cut that down, but in this case we're not, so run the tool. Okay, so now that our tool has completed running, let's look at our new feature class that we created, streets post. I'm going to open up the attribute table. So we know that since streets is the target feature, this table is derived here. The beginning of this table is derived from the streets. And then the join feature, being the post offices, that gets added on to the end of this table. So here we go. I'm not sure exactly where it picks up, but certainly facilities and the type of facility post office. So this is that part that has been added. This looks like possibly names of post offices. Going back to the beginning of this is that field that we created, the distance field name. And we're called this feet, but just to convince us that this really is feet, let's go and look at the units on this layer. So I'm going to open up streets post properties. We're going into the source. And just down here at the bottom, it tells us our vertical units are in feet. And the other thing to note about this is a straight line from each of these streets to the post office. This is, so essentially as the crow flies. This is not based on if you were on the street and how long it would take you making your turns and following the regular streets. So we want to symbolize this based on which of these streets is closest to which post office. So I'm going to double click on that to open up my symbology. We want to do unique features. So let me go back. So instead of a single symbol, we want unique values. So think for a minute why we would do unique versus graduated. Graduated implies some kind of a relationship, smaller to bigger, closer to further away. In this case, we're just trying to identify which neighborhoods belong to which post offices. So we're going to want to select our facilities in field. This is the name of the facility. And I'm not too into these pastels. So let's look for some other kind of unique. So these are just random unique colors that don't have a relationship to each other. Not liking that too much either, but let's do one of those. Yeah, I'm kind of liking that a little better. So it looks good. Each of the neighborhoods that's closest to these respective post offices have their own color. So take a look at figure 10.22 on page 329. That's the textbook version of this map. Yours should look like it or similar to it. So we just finished step 17. And on page 329, the book asks the question, how many streets are more than 2 miles from a post office? Now, I'm not going to answer that. I'm not going to demo it, but to give you a hint, this is not something in this chapter. This is something we've done many times. You're going to want to go through here and you're going to want to select which streets are equal to or greater than 10,560 feet, which is 2 miles. Something that we've done before. Okay, so now we are on step 18, and we're going to symbolize this in a different way. Instead of neighborhoods around post offices, we're going to do distance to post offices. So we're going to switch our field value. And in this case, instead of doing unique colors or unique values, this is going to make a lot more sense to do graduated colors because we're showing a change in distance. So it's like a continuous data field. Now, the one thing to be conscious of is if we open up our streets post attribute table and we look at this field, so I'm going to symbol on this field, PO distance feet, which is the new field we created. Each of these values is different, and we have 40,000 values, 40,000 different values. So if we were to symbolize that on unique values, it's going to pick a different color for each of those 40,000. So that's going to bog down your, it's going to bog down your machine. So if that happens to you, I would say right now, in fact, let's save. If it bogs down, it might lock up your computer. So you might want to watch, and if you try it, just be very careful. So I'm going to switch, instead of switching this field to the distance, first I'm going to change this to graduated colors, right? So I had just done this and it knew which field to pick. So it pulled up, because this is the last field I put in here with this color scheme. I got PO distance in feet. So this is what we're looking for. This looks about right. Really not liking this color scheme at all. So I'm going to change this to, let's just pick kind of a yellowish to blue. And again, default natural breaks. I want to just, I always like to try quantile. I actually kind of like quantile better for this one. So give this a try on your computer after you've saved, and you should have something that approximates the figure 10.23 in the text. So now this brings us to the last map we're going to make for this section. And we're going to turn off everything that had to do with post offices. Pull that up. And now the layers we're going to be looking at are rec centers and block population. So we're looking at two layers that are both point features. And think about it, the last one we did was points to lines, and the one before that was points to polygons. So the book poses the question for this problem: how many people are within walking distance of a recreation center? And we're defining walking distance as half a mile. So stop and think about this. So what do we want our output to look like? What's the cardinality? What type of join are we thinking about doing? So if we want how many people are within walking distance of the recreation centers, it makes sense that we would use recreation centers as our target. So we'll have a table with a list of the recreation centers. And then each recreation center will have a column that'll have a total or a sum of all the population, or the population that's nearby, represented by these points. So right off the bat, you know that our cardinality, this is not a one-to-one, since we have one recreation center and many of these different centroid points from the block population. So the cardinality is a one-to-many. So then we know right off that we're going to have to set up some merge rules when we do our tool. So our map is all cleaned up and ready to go. We're going to want to open our spatial join tool. So we go back to the geoprocessing pane and go back and open a brand new tool. So our target feature is the rec centers. Our join feature is going to be the block population. And then we're going to rename this centers block population. So I will do this my own way. Centers block pop. So we're going to keep our join operation as a one-to-one, even though on our map the relationship between the features is a one-to-many. We're going to force this into a one-to-one by setting up merge rules. We want to keep all of our target features. That's because we don't want to leave out any of the rep centers. And our match option, we're looking for, we're going to be summarizing the population within a walking distance of the rec centers. So our match option is going to be within a distance, this one. And our search radius, even though our map units are feet, we can change that. So 0.5, and we just select our units for miles. And now we have to set up our merge features, our merge rules. So we're going to eliminate a bunch of these fields to simplify what comes across. So we're keeping this one facility in. And then the next field we want is this pop 2010. So I'm going to Control-Shift, highlight all of these that we're going to get rid of, and hit an X. And I'm just going to get rid of this one. So yours should look like this: facility in pop 2010 and housing unit. And then this is where we're going to tell the tool to summarize our population based on this search. So merge rule is going to be sum for pop 2010 and also for that housing units. And run the tool. And our tool has run, so let's look at the table and see how it looks. So definitely a lot cleaned up with just a few fields. Facility N, no doubt that's the name, facility name. These are our rec centers. And then the sum of the population, the house units within our half-mile distance of each of these centers. And you can see the join count sort descending. Yeah, so our biggest one had 102 of these centroids in a half-a-mile radius around the rec center. And let's sort it the other way, down to like 1/10 of that. So let's symbolize this. Close our table. Turn off rec centers. And let's go through, right click and select symbology. So we're going to do graduated symbols. This is based on the population. So let's select graduated symbols here. Now this automatically selected join count as the field. So the bigger circles are the ones with the greatest number of the centroid, the block population points nearby, which kind of makes sense. So we're going to change this to Pop 2010. And let's make our minimum point a little smaller. That's plenty small. And our biggest one a little bigger. And I contend that with 5 different sizes here, it's pretty impossible to tell on the map the difference between, say, this size and that size. So I would reduce that offhand. Let's look at 4. Let's look at 3. A little easier. In this case, I would probably also do graduated colors. I would say these are our 3 biggest centers here with the biggest population nearby. And all of these, there's a big cluster of this middle size. Just looking at this intuitively, 3,500 to 4,000 isn't a lot difference, but then our next big break is over 8,000. So I would clean this up a bit, but for now, this is good enough. Just if you would turn something like this in for an assignment where you're being graded on your cartography, I would be very careful with these numbers and the way you display them. All right, so this is where we'll pause. And if you want to stop the video and go back and run through some of these steps, now is the time. And then we'll start with step 21 next. We are ready to go with our next few sections in the tutorial. And I am combining actually the next 3 together. And the reason we're doing it this way is for continuity, because they all build on each other. And it's essentially what you're learning to do in this is a suitability analysis. Your textbook calls it a sieve analysis or sieve analysis, which is kind of an interesting term. It's more of a geology term. But what we're doing is we're based on certain environmental criteria. We're using spatial analysis tools, and we are selecting the features that a snail, a black-billed snail, needs, and we're defining its habitat. So this is a really great example of how to use spatial analysis. And as you go on in GIS, you will come across this term a lot, suitability analysis. It's a sort of analysis that we see a lot that utilizes GIS. And the other thing about this, just to think about next week when we get into rasters, when we do chapter 11, we're going to do the same kind of analysis, but instead of using points, lines, and polygons, which are vectors, we're going to do the same analysis with raster. So it's a pretty interesting comparison. So open up your maps. And I've got probably more maps in here than what you have in yours. I have saved maps as I've been going at each step. So if I need to, I can go back and I can pick up where I left off and not have to recreate the map. So for our next part of the tutorial, open up your Sturgis area map. I'm going to double click. And I'm just going to go back here and I'm going to close out the Austin map since we're done with that. So now our task is to look for the best habitat for the black-billed snail. And there's 3 criteria that we know about that we're going to use in our model. We are looking for a geologic unit, that's limestone, dense coniferous forest, and an elevation between 1,200 and 1,600 meters. So we can use our tools to select the parts of this map that meet all of those criteria. So the first thing we're going to do is we are going to focus on the limestone units, and we are going to make a separate polygon layer for limestone units. In fact, we're going to go through and we're going to make polygons for each of the different criteria. So let's go into our geoprocessing tool and go back to the geoprocessing pane. And now what we're going to do is we're going to actually just create a feature class. We could do this by just doing a selection, but it's kind of nice to actually make a feature class out of a selection. It's a little more permanent. And if you want to use it repeatedly, if you're just exploring what you're doing, you don't have to worry about losing your selection. So I found my make feature layer. I'm going to double click and open that up. And our input feature is SD geology. And we're going to rename our output layer limestone. So we have to, before we create this, we need to essentially do our selection. So rock type is equal to limestone. Limestone. And run the tool. The tool has run, and here it is. This feature class is a subset of this SD geology feature class. In fact, we ran this exact same query a couple of weeks ago when we were learning the search by attribute tool. We did a search on limestone and we found all of the rock types that had limestone in the name. And just to double check, here's our rock type. Everything is limestone. And we can see that it's actually a number of different kinds of unit names that are this kind of rock. So for our next step, what we're going to do is create another polygon layer based on the vegetation. And what we want to select is a couple things. We want two different kinds of trees, ponderosa pine and white spruce. But then there's also another category in there. In fact, let's just open up the attribute table. So we're going to be looking at cover type. This tells us what kind of tree it is, and then density. So some of these mean ponderosa pine, and some of these mean white spruce. And then they have to be dense on top of that, which is going to be the C category. So we're actually going to have to do a query where we select three different features. So let's turn off everything except for vegetation. We're going to start over again with a new make features tool. So just clean the slate. And our input feature is going to be vegetation. Our new output layer is going to be conifers. And the reason we're doing this is because this is the kind of habitat snails prefer. Now we're going to select the right kinds of trees, like we were looking at in the table. So cover type is equal to, and we actually have the selection here in our drop-down TPP, which I believe is ponderosa. We're going to add a clause, and be very careful here with your operator. If you use and, it's going to have to satisfy both conditions. If you use or, which is the one we want, it can be either one. Cover type, and now we have to select the spruce is equal to TWS. Okay, so now we want to select these so that we also include the dense areas. In this case, we want to use and, because that means that both of these conditions have to meet the density requirement. Density 96 is equal to, I always check to make sure, C. So now we're going to do something to try to make sure that this runs these operators in the right order. So let's turn on our SQL code. And here is what the code actually looks like if we were to type it in. And what we want to do is make sure that it selects the trees first instead of running through this in sequential order. So what we're going to do is we're going to put parentheses around the first two SQL phrases. Of type and after TWS right here. So that'll make sure it runs these two first, and then from the selection we get from this, then it'll run this AND operator on that. So it's going to give us all the ponderosa pine, all the white spruce, and then from that selection, only those that meet this density requirement. So let's check our expression. It looks like we're good to go. Run the tool. So let's turn off our vegetation layer. Yep, and it looks about right. So check out the figure 10.25 when you run this and make sure that you get something that looks pretty similar to what's in the textbook. So now we have selected our limestone, our geology features that the snails like. We've selected the tree cover that the snails like, and the elevation has already been selected for us. I'm going to turn that on too. We don't have to prepare that layer, but that has already been set to snail requirements, which is between 1,200 and 1,600 meters. So these are all of the requirements for perfect snail habitat, and what we want to find out is where all three of these things overlap at the same time. That will give us our ideal snail habitat. Now, one thing we need to do, prepare before we get going, if you look close at this vegetation layer, there's lots of polygons here. And when we intersect, it's going to make the software run a lot slower if it's looking at each of these smaller polygons. So we're going to do a dissolve so we can combine all of these vegetation polygons together. Doesn't really matter to us at this point whether it's ponderosa or a spruce tree, because as far as we're concerned with the snails, it's the same thing. So let's go back to our geoprocessing pane and let's look for the dissolve tool. So we'll set up our tool. The feature we're going to use to dissolve is our conifers. And we're going to rename this to dense conifer. Dissolve, dense conifer dissolve. So our dissolve field is going to be this density 96, because we know that when we selected this, everything had to equal the condition of C, of the densest. We did select for two different tree types, so we want this final dissolve for everything to be the same. So we're going to dissolve it on a field that's identical for all of the features. So we're going to uncheck this create multi-part. We want them to be all a single part. And run the tool. So you can see the difference. Let me zoom in a little bit. If I turn off our new layer, the dense conifer dissolve, toggle it back and forth, you can see that it did indeed dissolve all of these polygons into one. So that's going to help our tool run a lot quicker. So we are ready finally to find out which areas are common between these three polygons. So we're going to open up our intersect tool. intersect. So we're going to list out all of the things we want to find the commonality for. So on the first drop-down box, I'm just going to go with limestone. And that gives me a second drop-down box. I'm going to go for the next thing, which is our conifer dissolve. And then finally, our elevation range. And we're going to give this a new name. Limestone intersect is not at all going to be descriptive. Snail habitat. And then for our attributes to join, yeah, so we're gonna select all attributes except feature ID. So that's at FID, and it's a unique number that the software assigns to new features. And since we're intersecting, it really doesn't matter to us what the old FID number is. So we're going to do all attributes except feature IDs. So this table is also in your text, figure 10.27. It should look the same. Offhand, mine does look a little different. I don't have an XY tolerance in here, and I think everything else looks the same. So it's probably just a difference of the version of the software. So let's go ahead and run this tool. And let's turn off our other layers and see what we got. So here is our snail habitat. This is where all of our features coexist. So just to get a better look at this, I'm going to turn on the layers, limestone, elevation, dense conifer. I'm going to change my snail habitat so I can actually tell it from everything else. Just make it something that's going to stand out. Yeah. So just toggling. Say it looks pretty good. Oops, wrong one. All right, so hopefully you have something that looks similar to this when you run it. And this brings us to the end of step 25 and the end of the section on using intersect for habitat analysis. So we're going to keep going. Our next section is overlay of lines and polygons. Now our task is to help these poor snails survive breeding season. There's a period apparently in early June when they leave their forest cover and they cruise out onto roads and they get run over and crushed. So Forest Service wants a map that shows primitive roads in relation to snail habitat. We have a layer of roads that has different kinds of roads, so we want to just look for the primitive ones. And then the Forest Service will close down those primitive roads to give the snails a break during breeding season. So first thing I want to do is I made my snail habitat this really bright orange. Let's make that something a little nicer. So I'm going to go with a deep green, actually a deeper green for now. That's a little more pleasant. And let's just turn on our roads layer and our snail habitat. If you have these other layers turned on, go ahead and turn those off now. We're going to use the select layer by attribute tool to select our primitive roads. So this is a tool we used quite a while ago. It's up here in our toolbar. I'm just going to go ahead and click on that, even though window is going to float over my display. So we want to change our input rows to rows. So our selection is going to be type, which is almost to the bottom, is equal to PR for primitive. And let's apply this. So zooming out, here's all our primitive roads. So we're going to go ahead and do an intersect on this. So I'm going to close my select by attributes table. Do not clear the selection. We're going to do an the geoprocessing, I'm going to start a new tool. Now we want to find out where our snail habitat and our primitive roads coexist in space. So let's start our input features, roads. Now remember, we have a selection on this, so this tool is only going to operate on the selected features. And then we're going to intersect this with our snail habitat. We're going to rename this proposed closures. Fix my L and run the tool. All right, let's see what this looks like. So let's clear our selections and zoom in. So I've still got my roads layer on underneath, and red appears to be the color for our proposed closed roads. So these do go right through snail habitat. Let's make this stand out a little bit better. I'm gonna make my line thicker. In our textbook, the roads are red, so let's make them stand out a little bit more. I think I'm going to change my snail habitat color now. Let's make that a lighter color. So that those two colors really contrast well. So there you go. You should have something that looks like this. I'm lining this up so it looks like the book, and this does look pretty much like what they have in the book. Actually, it looks exactly like what's in the book. So yours should look like something like this. Make a map, make sure all of this is readable, and leave your roads layer on underneath these other two layers. Actually leave it underneath your proposed closures, but on top of your snail habitat, so we can still see where all these other roads run through the habitat. This finishes the middle section. That was just step 28. What's actually 28 is save the project. So now we're done with 28, and we're starting the next section for our snail work. We're going to be combining overlay with buffer starting on step 29. So in this part of the tutorial, we want to identify the other roads and how they relate to the snail habitat. In fact, what the Forest Service wants to do is clear these thick forest stands so the snails aren't so tempted to get up to the edge of the road in the hopes that they stay away from the roads, they won't actually crawl into them and get run over. So now what we have to do is identify roads that go through snail habitat that are not the primitive, but the secondary and the primary. So the map we're going to make is going to show the stands that would potentially be cleared, and also determine the amount of snail habitat that we'd be eliminating if we actually did this. So we're going to repeat what we did before. We're going to do select by layer, select layer by attribute. So I'm just going to go up to this tool. And this time we need to change our input to roads. And we're going to select type is equal to primary. I'm going to add a clause. And again, be careful here not to use and. We want to collect both types of roads. So we need to use the operator or. If we did and, it would have to satisfy both conditions, and we would come up with nothing. So type is equal to secondary. So there's our roads, zooming out. So all of our secondary and primary roads are selected. So now we're going to buffer these, since the Forest Service wants to clear stands that are within 200 meters of the road. So let's go back to our tools. Let's search on buffer. We've used this tool before, not this week, but in the past week. Our input feature for buffer is going to be the roads. And again, we do not clear the selection. The tool is going to work on just the selected roads, which is exactly why we put these out. We're going to rename our output feature class road buffer 200. And we want to look for trees that are within 200 feet of this road. I'm sorry, 200 meters. And then the dissolve type, we want to change this from the default to dissolve all output features into a single feature. So we don't care that they're separate features. We want them to be all the same. So run the tool. So now that we've run our tool, we want to see where the snail habitats intersect with this road buffer. So back to the intersect tool. We're going to combine snail habitat with our road buffer. We're going to rename this proposed bin and keep everything else the same. Run the tool. And let's see what we got. Unfortunately, proposed thing came out the same color as my snail habitat, so let's change that. I'm just going to make it something that pops out at me. This is not what I put in the final map. Yeah, there we go. It looks pretty good to me. So these are all the areas that would potentially, let's clear our selection. And I'm going to turn off the roads just to make this easier to see. So these orange areas, turn off proposed closures because that gets a little confusing. That's all the same color. Yeah, so this looks good. So let's, if we were going to display this as a map that was useful to anyone, we would want to turn on our roads layer. And the thing that we really want to have pop out at us is this proposed fin. And snail habitat, I'm still not liking. I want to make that something that's there, but kind of more in the background. Snails to me are kind of olive green. That's way too olive green. Actually, let's make this transparent. I think that would be better. There we go. That looks about right. Zoom out a little bit. So here's our map showing our areas to be cleared. So the next part, and this is what's perfect for GIS, is determining exactly how much area we're looking at, because it's not necessarily a great thing to be going in and destroying habitat for an endangered species. So let's quantitate how big these proposed thin areas are. And this is a tool that we've used before. Let's go into geoprocessing, go back. Summary statistics tool, which we've seen many times this semester. Here's summary. I see it down here, summary statistics. So we're going to use this tool on our proposed fin. We're going to rename this thin area. Area. We're going to set our statistics field to shape area. Whenever the software runs a tool, it automatically keeps track of all this geometry. And our statistics type is sum. We want to sum all of the area. Now, this doesn't tell us or give us an option to change the units, but we know that the units are going to be in whatever unit the projection for this map uses. So let's just run this, and then we can see what kind of numbers we're looking at. Now, again, this is going to create a standalone table. Let's open this up. So one might ask, what unit is this? So let's go to proposed bin and investigate. So I'm opening the properties for that layer. Here's our source, meters. So this is going to be square meters. Now, that's not a super useful number, and it's also pretty huge. The book tells us that we can divide this by 1,000,000 to get square kilometers. You could always create a new field, a new column, and calculate this, or you can do it by hand. So that brings us to the end of this section. We just finished step 33. So let's pause here. This is a good chance to stop the video and go back and walk through the steps and make sure you understand everything. It's really reinforcing what we learned in the early part of this tutorial and stringing together all of these tools so we actually can do an analysis that's meaningful. Okay, so now we are moving on. We're going to work with a different kind of overlay function. It's called a union. This is different from intersect that we just finished with in that it combines polygons, and the result is a table that contains attributes from both sources. In contrast, when we were working with intersect, the output was only the area that overlapped in space. We were also able to work with all vector types, so points, lines, and polygons. So just to be sure that you understand, and if you have any questions at all, the textbook covers this really well. Look at pages 316 through 318. Just make sure you're completely confident you understand the differences between these different overlay types. Okay, so we're back at our map where we left it off at the end of the last section on step 33. Let's go ahead and prepare to start our next union exercises. So I'm collapsing all of the symbology. Our map's gotten pretty cluttered. Turn off the old snail layers that we were working on. This one. Okay. So we're going to turn on SD geology, and we also need to bring in a new feature class from the Sturgis folder. So open up your folders, your MGIS data. It's in Black Hills in the Sturgis Geo database, and it's inside this feature data set. We are looking for, it looks like slope %. So select this and drag it into your map. So let's zoom out and see what we've got here. So the setup for what we are doing is the Forest Service wants to do a study on landslides. So we're going to be looking at 2 different polygon layers for slope and geology. And between those two, that should give us an ability to predict landslides. So we're going to be combining these with the union tool. So we can see that our SD geology is this bigger layer. Let me turn off slope % for a moment. So there's our geology. And when we turn on our slope polygon, it's actually takes up about 3/4 of the same area. So before we dig in and we start using our new tools, let's take a look at our tables. That's always a good idea to look at tables before you start using your tools. So here's our SD geology attribute table. This should all look pretty familiar. It's a simple table. It looks like we've just got our geology units and the rock types, and opening our slope % table. an even simpler table. So it's just strictly our slope percent with the other usual features. Okay, so let's use our tool, close the tables. Now let's go into geoprocessing and back to the geoprocessing pane. And we want to pick union. So open up the union tool. So our input, for input features, we're going to add SD geology. And then next one is going to be slope percent. We're going to name the output geology slope. So we're going to make sure our attributes to join. We're going to keep all of the attributes, and we're going to want to do this as something you want to think about. It means that we're going to keep even areas that don't overlap up here. So there's a big section of the geology that doesn't overlap with the slope features. So let's go ahead and run this. So here is our output. Let's just start by taking a look at our new attribute table. So here is, I can see all the geology features that have come across, and going out to the right, this is where our slope starts. And note that under this FID, so feature ID number, that goes with the slope percent original polygon file, these all say -1. And moving down, there's just an area that says -1, and then we start getting some numbers. So what this means is this would be the area where there was no overlap with the polygon, or with the geology polygon. Let's just take another look at that. Yeah. I'm going to close this. So I just highlighted, right? So it's these features up here. And if I click on one of these and it brings up the pop-up, here's our slope, our slope percent feature ID number of -1. But if we select one of these down here, here we have a number. So it's telling us with that notation what's going on this table. So this is going to give us the ability to filter out these areas that don't overlap, which is exactly what we're going to do now. We're going to do create a new feature class from this. So close that window. And there's one other thing I noticed when I was looking at that table. Let's go back in and open up with this geology slope table. Here's our selection, the -1s on the slope layer, but there's also, I think, some -1s, yeah. So we have the same thing as happened on the geology layer, where there's the slope polygons, but no geology polygons. So these areas, it's certainly around the edge where the geology doesn't cover, and probably the slope does. So we're going to create a new layer. Let's clear our selection before we run another tool. Always remember to do that. And we're going to open a make feature layer tool. So let's go back, make feature layer, and open that up. So we want to work with our geology slope. We're going to rename this to valid combos. And we're gonna filter out all those -1s. So we have FIDs for both that we don't. So we're gonna select is not equal to -1. So there's the geology layer. And the operator we want with this is and, because we want it to be true for both. So our next fid, that's for the other layer that we used in the union, is not equal to -1. So for field info, we don't need to bring all these layers across. So it's a good time to clean up our table. So I just highlighted everything. There we go. Now I've highlighted everything. And I'm just going to check this box to turn them all off at the same time. And I'm going to go through and just select the ones that we want. So our text tells us we want symbol right here, competence, unit name, rock type, and slope percent. I think that's everything. Run the tool. And here's our new layer. So let's look at our new table. Actually, let's turn off this slope geology. So our original 2, and then our SD geology. So so this is the valid combos only, and it does look like we've successfully removed this area where we had geology but no slope. Yeah, and I turn on the slope percent, and you can see this little area down here where there's slope but no geology. And opening the attribute table, much more cleaned up. The FID numbers are gone because we didn't check those over here. We didn't bring those across. But a nice simple table with our slope percent. So it's pretty clean. It looks like we're ready to go on to the next step. So our first analysis, we're going to look for sinks. Sink, according to our books, is a collapsed area caused by rock dissolution. I think it's essentially a hole that opens up in the ground. So what we're looking for to define those areas are going to be limestone areas, which we've worked with before, combined with low slopes. So we're going to use our Make Feature Layer tool again, and we're going to export that based on those criteria. So let's go back to our geoprocessing pane and reopen up our Make Feature Layer to clear it out. And our input layer is going to be our valid combos here. We're going to rename this to sink hazard. And we're going to filter this for what we identify as what causes sink. So we're going to enter an expression rock type is equal to limestone. I don't want to take for granted that this is set to what I want it to be, so I always check it. And then, of course, we want to use the AND operator because we want both conditions to be true. Slope percent is less than 20, so that would be kind of a low slope. I'm just going to type in 20. Let's run our tool. Okay, let's take a look at this. Turn off valid combos and let's see what our sink hazards look like. Okay, so we want to make this a yellow color, so I'm just going to double click to open up the symbol properties, and we're going to turn this yellow. Okay. So our next area that we're going to identify is going to be rockfall. And what the characteristics we're looking for in rockfalls would be geology with stiff rocks. I'm not a geologist, so I don't know exactly what that means. But then the other is intuitive, any slope that's very steep. So let's go back and reopen our Make Features tool. So go back to geoprocessing pane, click the back button, open Make Feature Layer. So again, we want to start with our valid combos. We're going to name this rockfall hazard. And we're going to filter this. Competence is equal to high. Add a clause, make sure it's and because we want both conditions to be true. And slope percent is greater than 40. Run the tool. And we're going to give our rockfall hazard the medium orange color. So just double click on that, on the symbol. And medium orange to me is, I might change this later, but I think right now that will look different. Okay, so moving on. Now we want to look for landslide hazards or identify landslide hazards. And we're looking for weaker rocks with high slopes. So go back to your geoprocessing, do the same thing. We're going to reopen our make feature layer. Oops, I hit environments parameters. Okay, input feature, again, is valid combos. We're going to call this landslide hazards. And we're going to use expressions to filter our output. Competence is equal to low this time. Add the clause with the and operator. Slope percent is greater than 40. So that's our steep slope. Run the tool. And this time we're going to give it a dark orange color. So I'm going to double click on my symbol. And let's try that. And that looks about right. So we're going to do one last tool. Now we want to look at are roads that are close to rockfall hazards. So we're going to run the intersect tool this time. So go back to geoprocessing, hit the back button. I'm going to hit back one more time because I should have this in here. Intersect. So I'm going to open up my intersect tool. So we're going to intersect rockfall hazards with our roads layer. And we're going to call this rock hazards roads. And run the tool. So I'm going to make my road something I can see. Let's turn off, so rockfall hazard is what we use for the intersection. So I'm going to turn off my other layers and let's just kind of zoom in here and see what this looks like. And turn on the roads layer. Okay, so I'm going to turn off my rockfall hazards and my roads, and let's turn on the layers that we just created. And I think it's kind of helpful to have roads in there. So this would be our map from this part of the section. We just finished with step 42, and we finished up on our union section. And this is where we pause again. Definitely go back and rework the steps if you haven't done it already, and make sure you understand everything that we did. This brings us to our last section where we're working with slivers. As you noticed when we were doing the union between geology and slope, there was a lot of mismatching. When we're bringing in layers from different sources with different scales, there's going to potentially be a lot of mismatches, and there's a part of the tool is designed to compensate for that. So we're going to look at that next. So I have gone ahead and I've opened up my tolerances map that's comes with the maps with this project. Go ahead and open that now if you are following along. I'm going to zoom in, and we've got two different feature classes in here, the congressional districts in the yellow and the counties in the red. And you can see just right off the bat that there's a mismatch. And a big part of the reason for this mismatch is these different feature classes were built to be used at different scales. So you can imagine if we were to perform a union with these, there's going to be significant mismatch here at the borders. So let's see what that's going to look like. So let's go into our geoprocessing and open up the union tool. So we're going to perform a union on both of these layers, counties and CD114. We're going to call this Union 0 and run the tool. So here's the resulting feature class, and what it's done is it's picked up the symbology of this counties layer. So let's symbolize this so it is more obvious what's going on here. Let me pick a better color than that. Actually, to make it look really different, we'll go with blue. And I'm going to turn off these two layers underneath. So it's combined these two polygon layers, and from here it looks, you wouldn't know, but when you zoom in, you can see all these little polygon regions. And if I click on that, these are what we call slivers. They're mismatches between the two layers. This one here has a FID of -1, like we saw on the union of the geology and the slope layers. So let's go in and take a closer look at this -1. And remember, -1 means there was a no match between the two union layers. So there was, one was there and one wasn't. So let's measure this and see how big it is. So we're going to do our measure distance tool up in the toolbar. We're going to do planar is good. And yeah, let's do metric. So we're just going to measure straight across. So that's about 2,000 meters. Clear that. Here to here. 700 meters. Clear that again. Little, almost 900 meters. So you can explore around. Let's see if I can find, here's another empty one. Let me measure the distance there. Measure. Clear everything. 1,500. All right, so the point of this is that we can control this. We set the tolerances inside the tool, and we can do it logically by having an idea of the distance we want to set our tolerances for. It's still an estimate because there's clearly a wide variation. So I'm going to close my window here, my pop-up, and let's zoom out. And we're going to go back to our union tool, and we're going to run this again. So here's my my union 0. What we're going to do is we're going to set our tolerance to 500. And the unit is in meters because that's the unit of this layer. And It used to be that the tolerances you could set from the parameters window. For the new version, we go to environments. If you have an older version, you might see set XY tolerance here on in this window. So I'm going to go over to environments, and this is what we're looking for: XY values tolerance. So I'm going to enter 500. My units are meters, and I'm picking this. The book is giving us guidance that if you measure a whole bunch of these slivers, they're more or less roughly 1,000 meters. And we're going with half of that because this tolerance is giving us a radius. Let's see if this helps us here. Let's see, you would have to read through here. We're not going to do that right now, but we're going to follow the book's instructions, and we're going to try 500. The point is, it's an educated guess, and it's something that if you really wanted to make this perfect, you probably have to run it a few times with different tolerances, but this at least gets us into the ballpark. So I'm going to switch back to environments. We're at 500 because that's what our tolerance was set at, and we're going to run the tool. All right, so here's our Union 500. I'm going to zoom in again. And let's try to make this look different. Let's first just try, I'm going to turn this to a wider gray. So here's the old line, this red line. So if you look at this, it's a little more, it's just more generalized. The old line has more turns in it. So this is still a significant sliver, but it's being smoothed. So just to get the point across, let's do another one. Let's see, go back to geoprocessing. So we're going to change this now to 1,000. Oops, not 10,000. 1,000. Go into our environments and change this to 1,000 meters. So I'm going to turn that layer off. I'm going to clear that. Again, you can see this is, of course, a red line because it took the other symbology. Let's make it blue. And let me change this so that this is also no color. So red was the first one, and you can see all of these crazy turns in here. This black was the second one, the 500, and now blue is the 1,000. So note the difference between this. There isn't a sliver here anymore, whereas here there is. Let's get the information. See our fit, there's a mismatch here between the two layers that we joined. But now when we look at this, it's a complete match. This, I'm guessing, is probably, nope, that's also a match. So there's one sliver left there. So let's zoom out. I'm going to go back to the original layer. Let's just zoom out with this. So we've got a lot of generalized layers in here, but it still looks reasonable at this scale. And the source scale for this is these districts. And it was meant to be used at 1 to 5 million. So at this scale. So I'm turning off, there's the original source. And this is our last one with the tolerance at 1,000. So it's not too bad. There's still some issues here, but just keep in mind that this is a way you can control those slivers and eliminate them if you need to. And it really is a function of what scale you need to use the feature class at. And it's also a function of when you're joining different layers, what scale was each feature class meant to be used at. And it's the issue you have when we're trying to combine things that were designed for different scales. So that brings us to the end of this tutorial. We are done. This was step 47. Save your work. Go back and rework some of these last steps so you understand what the concepts were. And in general, the concepts that we learned on this tutorial are going to be part of the exercise. And as always, when we get to the exercises, instead of step-by-step guidance, this is where you're going to apply what you learned in the tutorials. So if you've gone through the tutorials and you've understood what you've done, you can pull on that knowledge when you're trying to figure out how to answer the questions in the exercises. And you can always go back and review the steps in the tutorial, because I guarantee you, you'll be able to pull from those examples and apply them to the questions in the tutorial and answer the exercise questions.